So this is the second part of undamped free vibration lecture. I delivered the basic lecture on undamped free vibration, and this is the second part of that lecture. So that it is continuation of first lecture. I will take some example on that for further briefing, and various aspects which relate to this undamped free vibrations are will be seen here. Okay, so let's consider the spring mass system having. Let's take some example of that. Okay, so mass is taken 2 kilogram. K is equals to 32 Newton per meter. So finds the equation of motion when the system is initially displaced 0.1 meter and an initial velocity of 0.5 meter per second given, and then find the natural frequency of the system. So here we idealize the structure as spring mass system, and considering this axis as the point of reference, that is zero initial displacement. Then from this, x naught is given, and positive direction consider this direction and negative to this direction. And the material stiffness given here in the form of a spring. And the lumped mass is M, and the surface on which the mass is sliding is frictionless. Okay, so that the normal component of force and does not affect the horizontal motion of the mass. But if there is a component of friction force that can affect with mu n is the part which includes to the analysis. Okay, so and the mass is accelerating in this direction. Okay, in the positive direction. Okay, so the governing equation for the particular this system, okay, is mx dot dot of t plus kx t is equal to 0, and the initial conditions already provided. X naught, which is equals to x at time t0 is equals to x naught, which is given as 0.1, and x dot of t at time t is equal to 0, which is x dot naught, which is 0.5 meter per second, which are already given. So this is the kilogram equation and the boundary condition or initial condition, sorry. Here we cannot talk about the boundary condition, but only initial condition. So the equation of motion for this system, substituting the mass and the stiffness K, we have this equation of motion. Okay. So the proposed solution for this case is let we assume x of t, which is equals to a lambda t. This is the exponential form of solution is assumed, so that for this x dot, the first derivative is equals to a lambda t, and the second derivative x dot dot t, which is a lambda square a lambda t. Okay, let's substitute this value into this equation. We can get this equation. Okay, a lambda square a lambda t plus a 16 e lambda t, which is equal to 0. Okay, so the characteristic equation from this is lambda square is equal to minus 16. This implies that lambda is equals to plus or minus j 4. This j is the complex number representation here. Okay, so the solution will be, now we have two roots. The lambda roots are 2 here. So because of that, the solution becomes given again in the form of, in the same form as j radical 16 e to the power of j radical 16 t plus a2 e minus of j radical of 16 t. A1 and A2 here are some arbitrary constants. So just simplifying the radical 16 term, which is 4 rad per second, that is the natural frequency. Therefore, the solution becomes this, okay? And then initial conditions will be imposed to this solution in order to find this A1 and the A2 values. So let's take this equation, and this is our equation. So just recalling the relation between exponential and the trigonometry, that for the complex form of mathematics, applying the Euler's formula. In Euler formulas, we have these relations. E the power of j alpha implies cos alpha plus j sin alpha, and e the power of minus j alpha is equal to cos alpha minus j sin alpha. So writing this equation in terms of these variables, we have this relation. Okay, in terms of e the power of j omega t, actually this is omega n. Okay, this all omegas are omega n. It is not, it is the natural frequency of the material. So we substitute those values. Finally, we can get this kind of relation. And for this relation, we can let A1 is equal to A1 plus A2, this component. I mean, okay. So this component is substituted by A1, and this is substituted by A2. Okay, then we can get this equation. Okay, so by applying this initial conditions, x naught is equals to A1, that is 0.1. and x naught dot is equals to A2, which is equals to the x dot, that v initial velocity over omega. So our omega is 4. Okay, so substituting these values, we can finally get this equation. Okay, these are the numeric values. Okay, so that is equivalent to is 1 over 10 cos 40 plus 1 over 8 sine 40. Actually, this, we can separate it like this. So this can be we can represent the solution in a single cosine or sine function rather than both sine and cos, because sine and cos are only in pi over 2 phase difference. So we can represent them in terms of one constant, so that this one constant is equal to a1 square plus a2 square. This means which is equals to x naught square plus v naught over v naught over omega n as a whole square. Omega n as a whole square. So that is the amplitude. Okay, that is A is this one. Our A1 is equals to x naught. Okay, our A2 is equals to x naught dot over omega. So using this relation, we can define A. Now we can define again the cos function. So sine is equals to opposite over hypotenuse, and cos is equals to adjacent over hypotenuse relation. We can define the phase angle pi. This phase angle pi in between constant 1 and so from that we can get pi relation. Okay, so this is our general equation. Okay, so our pi will be actually this 8 over. I can define pi here. Okay, phase angle pi is equals to tan inverse of A2 over A1. So this means which is equals to tan inverse of V naught over x times omega n. X times omega n. That is the pi value. Now let's see how we can find the natural frequency for various types of systems. Let's see. Okay, and the solution we obtain, this is a general form of solution. On that, this omega is the natural frequency, okay, or frequency of oscillation, and it depends on the characteristic of the oscillating system. This omega is frequency of oscillation omega is depend on the characteristic of oscillating system. That is why it is called the natural frequency of oscillation. It doesn't affected by a static system, but most dynamic system in the equation, in our equation, the dynamic part of equation affects the natural frequency, but the static part does not affect. So it is called the natural frequency, and it is represented as rad per second. Okay, and the frequency of the time frequency of oscillation, Fn, which is equals to omega n over 2 pi. Okay, so both this omega n is equals to 1 over okay, omega n is equals to 2 pi over okay, f. No, 2 pi times f, sorry. 2 pi times f, fn. Omega n is equal to 2 pi over fn. Okay, so it is rad per second over rad per cycle, 2 pi rad. In every cycle we have 2 pi. So which gives us omega n over 2 pi hertz. That is the time frequency of oscillation. So sometimes we analyze the system in time domain, or sometimes we analyze it in the frequency domain. Okay, so this time is equal to 2 pi over omega n. That is the time period of oscillation. It is oscillation period. T is equal to 2 pi over omega n, which is in second. Okay. Amplitude and phase are here. We can represent. Okay. The same thing. What we have discussed there, all are here. Okay. This is when we make some rearrangement of this, multiplying and dividing it, the terms, we can get this type of equations. This is maximum amplitude for this sine or cosine representation. Okay, the phase is tan of tan pi, which is tan pi over cos pi. So that represents pi is equal to tan inverse of this term. Okay. So this is a simple representation of simple harmonic motion. So the time period from here to here, which is 2 pi. This is 2 pi. Okay. That is one period. Okay. Here we can see the initial slope at the point where x naught starts. That is known as slope, which is x naught dot. That is v naught, initial velocity v naught. Here x naught is initial displacement, x naught is initial velocity, and from here to here, the natural time period, tau n, which is 2 pi over omega n, is the natural time period in the time domain analysis. This is frequency domain analysis. Okay, analysis are frequency domain and time domain. So here it is in terms of time. We represent it in terms of time. Here it is in terms of omega nt. This is frequency domain. Okay, so in the frequency domain, the initial pi, the phase angle pi, is equals to that what we have derived. Pi is equals to, okay, radical of, no, not radical, but undo. We can remove this. This term, it is just this term. This is actually a reverse. This is v naught over x naught. X naught, v naught. So we invert it, and finally we get v naught tan inverse of v naught over x naught omega n. This is the phase. Okay, so this is time domain and frequency domain. So here we consider this distance pi over omega n. This distance is taken as pi over omega n in the time domain analysis. But in the frequency domain, it is simply pi. That is the phase angle pi. That is the only that are the difference. So this is the oscillation of free vibration. Okay, now so we are generalizing this free vibration case for single degree of freedom. The governing equation assumed solution, amplitude, okay, phase angle, okay. So different ways to write the solution. Okay, so we have different ways. Someone can write it in this form: a sine omega t plus pi, which is equal to this term by solving the initial value part, we can get this equation. Sorry, this is not a bigger bracket, it is a bracket like this. Again, another person can write it like this in both sine and the cos term. That is equivalent with this solution by substituting the initial values. Again, another person can write, this type. This is the exponential complex form, okay, in terms of e the power of. So that will be in the form of, again, for this, there is this kind of bracket. No bracket required. This one is within this bracket, and this one is within this bracket, okay. Or we can represent in the cosine. Here it is in terms of sine. Similarly in cosine, because cosine and sine having phase difference, so this minus indicates that they have phase difference. A similar approach. This constant terms should be placed in separate brackets. Okay, these are type of representation or solution representation. Some useful quantities in the analysis. So A represents the peak value of the amplitude. Okay, that the maximum amplitude is represented by A. The mean average values of the position, mean square values can be represented in this form using limit as limit of t approach to infinity. Approach to infinity is here. Here also t approach to infinity. Okay, so root mean square value representation, which is given in this form, and this displacement, which is x max A, velocity x dot max, acceleration x dot dot max, which is given with omega square A, omega A, and simply A. That is a representation. So this is similar term which we have discussed. Okay, so these are the time domain that pi is represented by pi over omega n. Okay, so now let's see some important aspect of the effective stiffness of various kind of models. As we know from the strengths of material concept, the stiffness is force is equals to force in the spring material is equals to the kx. That k is the stiffness of the material, and x is the deformation, or k delta. Delta, we can take this as delta or. So the strain energy on the material is equals to half kx squared. Okay, U is equals to, for example, area under this graph is strain energy or spring potential energy, which is equals to half kx squared. Okay, kx squared. Okay. So how we can find the effective stiffness constants of various vibrating structure. For example, this is a linear kind of bar, which is having a lumped mass m, and stiffness of material having EA over L, which is directly obtained from strengths of material, and the length of the bar is equals to L, and which is vibrating in this direction. Then how we can find that K AE over L is one of the stiffness of this system. Again, the stiffness of torsional system, similar to this. This is so G, this G is the shear modulus of the material. This is Young's modulus. This is area of the cross-sectional area and the length. G is the shear modulus. J is the polar moment of inertia. And L is the length of this thing. So Gj over L is the torsional KT. I can say these are KT for the rod, which is subjected to testing. The helical spring, which is under compression and tension, okay, which is subjected to compression and the tension is represented with K is equals to G D square over 64 NR square. This N is number of turns in the helical spring, and the G is the shear modulus of the spring, and R is the radius of turns, and D is the diameter. Okay, so that is the effective stiffness of this system. So for the system having a cylinder system, which is kind of long, so we model it with this type of representation. This is a representation equivalent with this. Okay, So 3ei over L cube. I is the moment, that is the moment. Yeah, so these all are easily obtained from strings of material actually. And the natural frequency is K over, as we know, radical K over M is the natural frequency. So here M is already included under radical. So that is the natural frequency of this system or cantilever beam. And this is similar approach. The effective stiffness KT MT over theta or phi GD the power of 4 over 32L for this part. Okay. Again, for the spring, it is AE over L, area of the cross section of this thing when we cut it from here. E is the material youngest modulus of material. L is the unstretched length of the system. Okay, so natural frequency of oscillations for various systems. Again, this I defined it already. Okay, this is already defined. This is again second time. So let me pass this. Natural frequency of this type of system, that is already what we have discussed. And actually here there is equivalent concept. Sorry. When we say equivalent, there may be a mass of spring considered. In a simple assumption, mass of spring is not considered. But if you consider the mass of the spring material, then we have to consider equivalent mass. Again, if there is some other stiffness, because here it is only one spring, but sometimes springs come in parallel or springs come in series, then equivalent spring. So this system can be replaced by this for the system having some additional feature. This one also represented like this because K equivalent over M equivalent. So K will be found. We will see how we can find K in series and K in parallel. Again, how the mass can affect the natural frequency of the material. So this is the part. Okay, so here, this is a torsional system. Okay, and this is the shaft, and there is a disc here. Okay, and these are the axes of reference are there. So J naught theta dot dot is the mass times acceleration part of linear case, and the torque is applied here. MT is the torque. Okay, so from the theory of torsion of circular shaft, we have MT is equal to KT theta, which is GI naught over L theta. So that I is the polar moment of inertia. Okay, I is the polar moment of inertia in this case. Okay, this is the mass moment of inertia. G is the mass moment of inertia. Mass moment, and I is polar moment. Polar moment. Okay, so we can represent G naught is equals to like this, and KT is G pi d the power of 4 32H. These all concepts are there in the book of strengths of material, like many strengths of material books will provide these formulas. Okay, let's see the natural frequency of simple pendulum. Okay, applying Newton law for this free body diagram, we consider actually this massless or massless bar or cord and frictionless at the attachment, and this mass is vibrating and which obeys conservation of moment, conservation of energy. That is, energy at some point equal to energy at second point. So based on that, applying the equation of motion in the t direction. T is this direction, that is tangential. This is normal direction. So ml theta dot dot acceleration in the t is ml theta dot dot. Inward direction, the tension is equal to ml theta dot square. And there is mg which is acting downward. So applying this mg sine theta. So this mg will be resolved also. Here we can resolve mg to this direction and to this direction. There is theta here. So this part of mg is mg sine theta. Mg sine theta. And this, the one which opposite direction to the normal, is mg cos theta. So let's take mg sine theta, which is equal to ml theta dot dot. So just assigning these two terms, we can get this equation. From this, finally, what we can get? Yeah, just it is a simple rearrangement. Theta dot dot is equals to plus, mg. Just consider this sine theta is equals to simply theta for a small value of theta. Mg over ml theta is equals to 0. So from this, m is cancelled by m, we have left g over l. So theta dot dot plus g over l times theta is equals to 0 is the equation. This g over l is equals to the natural frequency part, as we know that k over m is equals to omega n square. This is equal to omega n square. Okay. Omega n square is equals to, from this equation, this is omega n square term, which is g over l. So then omega n is equals to radical of g over l. Yeah. So this is what. Okay. Again, for compound pendulum, we can find this thing in the book of mechanical vibration, SS Rao. We can find this object. So for the compound vibration, we can find this is equation of equilibrium or linearized equation of motion, and the natural frequency is mg g over j naught. Okay, so this is the distance between pivoting point to the center of gravity. D is the distance. Okay, here. Okay, so natural frequency is gd over k naught. That this is in terms of radius of gyration. Okay, j naught is defined in terms of, that means j naught is represented by substituted by radius of gyration. Okay, then we can get this. Another natural frequency of spring mass system, especially here we can see K2 and K1, two mass. No, mass is subjected and suspended or placed in between two springs. So whenever one of the spring is compressed, another spring is in tension. And due to that, our equation becomes having K1 plus K2. How we can get that? We can make a free body diagram of the system, and we can produce equilibrium equation. Then finally, what you can get is K1 plus K2. Now we are expressing it in terms of equivalent stiffness. K equivalent is equal to K1 plus K2. So our mass is 1. Well, we didn't consider mass of these things. So that K1 plus K2 over N is the natural frequency. Here we have two springs in series, and then mass is placed in between. Then again, third spring is there. So still we have to find the equivalent stiffness. So for the two stiffness in series, we have a relation that for these two only, 1 over K is equals to 1 over K1, and the K2 is equals to 1 over K1 plus 1 over K1 plus 1 over K2. K2. Sorry for the writing. Okay, this is equal to this K2, K1, K1, K2, K1, K2 component. And then when we go to up, another spring also there. We'll add up this one. This spring constant plus this one gives us the, this is K1, K2 over K1, K1 plus K2 plus K3 is the component of equivalent stiffness. So K equivalent, this is K equivalent. So omega n is equal to K equivalent over N, which gives us this equation. Here also the same. We have two bars having different cross section in series. So the torsional stiffness KT1 and KT2 are provided, and the third, this is 3, KT3. This is KT3. This is KT2, let me say. This is KT1. KT1. Okay, let T will be added. So this is the system of equivalent K. Okay. KT equivalent is equals to these terms. Then this is the natural frequency. Again, we have here a number of pulleys and the spring systems as well as mass systems are there. Most of the time, maybe the weight of pulleys are not considered, and other components are not considered. So this complex system, how we can do that? At the very beginning, we'll take a cut from this, the free body diagram. We'll make a cut from here and here. So we can see F at center. Okay, for this system, K delta F in this direction, K delta F is equals to T1 plus T2. The tension here, T1 plus T2 here. Okay, from this relationship, we can find this delta F is equals to 2T over K1, because this is the K1. 2T over K1 is our delta F, or 2 times T is equals to K delta F. Okay, so from this relation, again, let's take another section having center C here, pulley center C. Okay, here pulley mass is not considered. Okay. In all cases, pulley mass is not considered. Okay, here 2T is downward, K delta C is upward. Okay, this delta F means the deflection at point F. Okay, so again here K delta C, which is equivalent with T1 plus T2, both of them in the minus. So then delta C is equal to Tt over K2. Delta F is equal to this. Okay, second equation. Now, a relation of displacement of mass. Okay, x is equals to 2 times of 2t plus k1. That means for the first, this one, plus 2 times t, 2t over k, because of this second, which gives us this relation. Because we will substitute each of, just rearrange and multiply, we can get this equation. So solving for the tension, T is equals to this. Here again we have some another relation. Okay, at AM, that mg is here, that is mass. Okay, so rearranging these all terms, finally what we can get equation of motion as mx dot dot times k1 k2, this part t, mx dot dot t, which is equal to mg. Okay, so here it is also this mx k1 k2, 4 times k1 plus k1. This is k1, it is k2, sorry, this is k2. Here it is k2, this mistake, k2, k1 plus k2. Yeah, it is k2 here. Again, here it is k2. So solving, finally we get omega n is equals to this, because this is our equivalent stiffness. Another thing is equivalent system in series and the parallel. When the springs are in series, they add the stiffening effect. So that they are the summation of ki's, k1, k2, k3. Okay, so K equivalent is equal to the sum of all k's. But if they are in series, here they are in parallel, but here they are in series, that it increases the flexibility of the system. So that it is represented with 1 over summation of k. That means in this case, we can do 1 over k equivalent is equals to k1 plus 1 over k1 plus 1 over k2 plus 1 over kn. But in this case, it is simply k1 plus k2 plus k3. Yeah, this is a good representation for spring in series. And this is for spring in parallel. Okay. So let's see some whether the effect of free compression in the system affects the natural frequency or not. Okay. So let me ask some question. Just write down whether natural frequency is different or the same when the system is excited with external force. Let's see the free body diagram here. Here K1, K2. So assume that some L here. So half of L to this side, L over 2 is to this side, and L over 2 that side, and this is considering the inertial coordinate axis, that the point of inertial coordinate axis. Then applying Newton's law, what we can get is mx dot dot plus k1 plus k2 x, which is equal to k1 minus k2 L over 2. So the equation of motion here is non-homogeneous due to the presence of the constants on the right-hand side. So on the left-hand side, it is a function of x. Okay, k is a function of x, m is a function of x. But here there is no x term. It is constant. This is constant, which increases the non-homogeneity of the system. So the pre-con question, can anything to do with the natural frequency? The answer is the external force has nothing to do with the motion coordinate in a given problem. It does not affect the natural frequency. The term K1 minus K2 over L2 comes from external free compression, and we can separate them out, and they are not a function of x and cannot affect the natural frequency. So our equation mx dot dot plus k1 plus k2 x. Okay, so in this part of the equation, there is no acceleration term. So that part taken for the static deflection test. Okay, this k1 plus k2 times over k1 minus k2 L over 2 is the static deflection condition. And we consider the total x, which is equals to the dynamic deflection plus static deflection. Then when we derive one time, this gives dynamic derivative, but static will be 0, that is constant. X double dot is equal to x dynamic double dot. So substituting this equation, just we are proving whether it affects our system or not. So by substituting, we can get the dynamic part here and the static and constant term part here. So from this relation, we can see x static is equals to k1 minus k2 over L over 2 times over k1 plus k2. That is a static term. So just to summarize this today's lecture, write down the equation of motion using Newton's law. Someone can write it using the energy law, conservation of energy law. Someone can write it using D'Alembert's principle, and so on, and solve the equation of motion for single degree of freedom system for undamped case. B, use initial conditions to determine amplitude and phase of vibration of single body diagram. Again, evaluate the effective stiffness of structure and members. This is as an assignment. Again, here, the amplitude of, these are also again assignment questions. So please, any interested body can do these examples. And if possible, you just send solution in comment section. Okay, for these 3 questions, I need solution from you based on the discussion which we have made today. So this is all about today's lecture. Thank you very much for attending this lecture, and just give comment or any kind of, if I made any mistake, just highlight it and tell me. By doing that, we can improve our lecture.